Good morning, Amlan Kar sir.
Yeah. Good morning, Amlan Kar sir.
Yeah, good morning.
Shall we start?
Okay.
Yeah. Hello, everyone. I welcome to the today's session of short-term course on emerging technologies in processing of advanced materials and its characterization. I would like to introduce today's presenter, Dr. Amlan Kar. He is assistant professor in Indian Institute of Technology, Dhanbad. Dr. Amlan Kar has completed his PhD in Mechanical Engineering from IISc Bangalore in the year 2017. He completed his PhD thesis on micromechanisms associated with friction stir welding of aluminium with titanium. His PhD thesis, a DRDO India sponsored project, deals with elucidating different micromechanisms associated with friction stir welding of aluminium to titanium with and without interlayer. He was awarded the prestigious IIM SJEF fellowships to the MTech student for the duration 2019 to 11 during his MTech in IIT Madras. He has involved in various projects which are sponsored by DST, Boeing India, IISc Bangalore, Osaka University, etc. His research interests include severe deformation processes, metal forming, friction stir welding and processing, solid state additive manufacturing and hybrid manufacturing. We would love to hear from you, sir. So the session is handed over to Dr. Amlan Kar, sir.
Yeah, thank you, Nanda, for the introductions. Okay, I just start my presentation. It will be good. Okay.
Narendra sir, kindly unshare your screen so that Amlan Kar sir can share the screen.
Yes, sir can share it, sir.
I hope a good morning to all, and I'm happy to be here. And thanks, Moise, for the for your invitations. Today, I am going to discuss some of the topic associated with dissimilar friction stir welding and some of the advanced characterization method I have performed. So I will discuss all of this. But before going into the presentations, I will acknowledge my previous supervisor, Professor Satish P. Kailas, Professor Sattam Subhas from IISc Bangalore. And after that, I have done my postdoc under the guidance of Professor Rustam Kaibasar and Professor Hideshwari Puzi. So whatever I have acquired knowledge, that they have immense contribution to that. So this is the layout of my presentations. I will be discussing about some of the characterization techniques in part 1, and followed by how we can apply this characterization technique in applications. Like here I have pointed out 2 examples: friction stir welding of aluminum to titanium, and effect of titanium particle on high temperature grain stability of composite material. In part 1, there are different characterization technique available when you are when going to understand the structure property correlations of any materials. Okay, this characterization technique is not associated with only welds. This could be associated with any sort of a process. So there is X-ray microcomputed tomography first, and followed by I will discuss about the EBST characterization technique that is called electron backscatter diffractions. And there are a few other techniques I will discuss, that is chemical analysis, finite element simulations, and how you can interact or how you can correlate the structure with the mechanical property of the weld. The three things which has been colored by red color, I will not discuss in details because it has already been covered in the earlier lectures. But we'll discuss in part 2 and part 3 how this could be useful in understanding the behavior of the material when it is subjected to external loading. So part 1, this is microcomputed tomography. But before going into details or before going into the discussions, let me take you to some of the video available in open source, so that you can understand much better or animation wise how it works. Okay. So that
if you want to look at the inside of an apple without cutting
just look at the video,
probably use X-ray technology.
So that you can understand much better.
Micro-CT systems, it's impossible to image the apple seeds inside at the highest resolution unless you slice the apple. Only when the apple seed is moved close enough to the X-ray source can you see its microscopic details. The ability to image the apple seed at submicron resolution without the need to cut the apple illustrates what we call resolution at a distance. Conventional micro-CT solutions work with geometric magnification. The farther the object is from the radiation source, the lower the resolution. Therefore,
Sir, sorry for interruption. We are not getting video.
Yes?
We are not getting video.
Oh.
Sir, sir. I'm getting video. Maybe it's our side problem.
Okay. Anyhow, whoever is getting, so you just look at it. So after that, I will discuss in details, okay?
Of larger objects is limited because the size of the sample itself requires increased distance. Zeiss X-ray microscopes enable submicron imaging at large distances. Initially magnified via geometric projection, the X-ray image is converted to visible light, which then is magnified by microscope optics. Now we clearly see the hidden details. The size of the sample is no longer a barrier. X-ray microscopy with resolution at a distance opens up possibilities for new insights in many fields of application. The study of aging effects in battery cells over hundreds of charge cycles. The microstructural analysis of printed materials. The exploration of new materials under environmental conditions, and many other applications. Electronics quality control, roughness measurements, building materials, 3D crystallography, raw materials, and organic structures. How can you use resolution at a distance in your work? Learn more about Zeiss X-ray microscopy.
So we have understood that this is the demographic, this is the technique on which you can see, you can visualize the informations available inside a material. Okay, and there is no boundary in terms of resolutions. Okay, resolutions depend on geometric resolution as well as optical resolutions. And as I have mentioned here, this XCT, the microcomputed tomography, is an X-ray tomography technique with some micron resolutions, typically using an X-ray tube with cone beam geometry as a source, and the sample, is there, you can see it subjected to continuous rotations, and during rotations, at a different frame, you get a different two-dimensional images. By computerization technique, that two-dimensional images has been extracted, and that has been computerized in such a way that we can get a three-dimensional object. And it is also considered as a non-destructive technique, because you do not need to cut the material, okay, to see the informations available inside the material. And it can be used in during the operations, or it can be used during in situ studies, like phase evolutions during some sort of process like a heat treatment, okay, or during tensile testing. That also can be studied with the help of micro CT scan. Okay. And as I have mentioned here, you can see the three-dimensional image, and which can reveal the volume, shape, or spatial distributions, or the concentrations of the second phase inside a material. Okay, and also, since you know all the informations available inside the material, then you can find out the interrelations, correlations. Okay, or is there any defects available inside the material or not? Okay. So, but from the basic point of view, from the structural point of view, it is a X-ray method. Okay, so same can be used for neutron study also, neutron diffractions. It's a diffraction method. And since we are talking about the X-ray computed tomography, that follow Lambert-Beer law. What is Lambert-Beer law? You can see here, I have already mentioned, I is equal to I naught e to the power minus nu x, where I is the transmitted intensity, or I naught is the incident X-ray intensity. So this is the initial incidence intensity of the X-ray, and I is the transmitted intensity. And this nu is the linear attenuation coefficients. This is very, very important term. Okay, why? Because that define the characteristics of the component or the element. Like when you have a multi-component material, each material having different attenuation coefficients, and because of the differences in the attenuation coefficients, we can characterize the element inside the material. Like in case of BSC image in ACM, how you can characterize the different elements? By contrast. Yes or no? By contrast. So here, the difference in the linear attenuation coefficient actually prove the element, and X is the thickness of the sample. And as I was discussing, the LAC not only depend on the element, it also depend on the density and the atomic number of the material and the applied X-ray energy. In ACM and any optical image, you generally define the magnifications. Okay, as in the video also, as in the video, it is shown the magnification is dictated by the geometric magnification, actually dictated by the distance between source to the detector and the source to the object. The same has been mentioned here. This is the magnifications. And apart from that, you can see that magnification also depend on the projector lens. So the additional projector lens has been embedded over here in the instrument to magnify the image. In the previous slide, I was discussing about the linear attenuation number. But in actual practice or in computer, they cannot see the linear attenuation coefficients. This Hounsfield number is calculated from the linear attenuation number. So this is the equations you can see. In the computer, they calculate the Hounsfield number. From there, in each point in the 2D image, if you see in a 2D image, the resolutions in each point has been specified with the help of Hounsfield number. And Hounsfield number is calculated from the linear attenuation coefficients of the element. So basically, that is the correlations between the Hounsfield number and the atomic number of the element. And this is another example, another equations which is used to find out the resolutions of the component, resolutions of the image. And in 3D image, it is called voxel. It is not the pixel. It is called voxel because it is three-dimensional block. The size of the voxel, that is the resolutions, is calculated with the help of this equation. R is equal to d by m plus 1 minus 1 by m into s. So here d is the resolution of the detector, because detector is nothing but a photophosphorus screen. So it has particular resolutions. Okay, that also you have to know, or you have to calculate. So that is taken into account to find out the resolutions of the image which we are getting out of this calculation, out of these characterizations. So inside the X-ray tomography machines, that is Jesse's Versa machines, you can see one X-ray, and there is a round rotating tables which is rotating the sample continuously. And at each step of rotations, we get a two-dimensional image. This two-dimensional image is back projected, and with the help of computer reconstructions, we get a three-dimensional volumetric image. This three-dimensional volumetric image can be analyzed based on their compositions. And you can find out how much the ports is there inside the material, or which particular element is there inside the material. So how you do that? Here, there is one example. You can see it is a black and white image. From there, you have to find out that the particular element, how it is dispersed into the material. Okay, in the material. So you got a three-dimensional image based on Hounsfield number. You get a contrast. Then you have to find out the particular contrast. Here you can see particular contrast has been found out, and after the reconstruction, you get the complete informations of this particular elements, how it is dispersed in the material. Here is an example of XCT images. You can see in ACM image, you can see the compositions. Okay, this is the silicon. This is the composite material, and where the silicon carbide particle is dispersed. Okay, and you can get the image informations, and that has been reconstructed in XCT, and then you can find out the three-dimensional distributions of this particular element in the material. Similarly, you can see the bottom image, you can see that Ti64 5% titanium TiB whisker metal has been dispersed in the metal matrix composite. So here you can see some of the whisker element like this black elongated particles. This is the titanium boride particle, and that has been dispersed in the alpha titanium. Okay, so with the help of XCT, you can find out how it is dispersed in the material, and from there we can correlate the interrelations or the boundary interactions, how it is interacting at the boundary with the particular elements, okay, in 3 dimensions. The next advanced characterization technique which I am interested to discuss here, that is the electron backscatter diffraction, that is the EBSD technique. From this image you can easily see that this is nothing but a ACM microscope, the scanning electron microscope, and the sample is inclined at a particular angle. Generally it is inclined at 60 to 80 degree. Because of the inclinations, what happens? The incident electron is interact and the backscatter electron is come out of the sample because of those interactions with the nucleus of the element. And because of these inclinations, a maximum fractions of the backscatter electron is come out, and that has been used, that had been characterized properly to get the information about the orientation of each plane, okay, or the crystallographic textural orientations informations. It's provide versatility in mapping orientations, crystal type, perfection over a wide range of step size, making it a powerful microstructural characterization tool. So basically, it gives the informations about the orientation of the plane with respect to the incident angle or with respect to the sample orientation. Okay, so from there you can correlate the external parameter with the internal textural crystallographic information. So basically, it links the microstructure, crystallographic structure, and therefore we get a very good quantitative informations like which direction the plane is oriented, and based on that we get a different anisotropic property of the material. But how this how this crystallographic structure been formed? So you know, when the incident electron is impinged on the material, then it's diverse, and because of the divergence you can see there is a different plane is there inside a material. You know, the grain is consist of a plane or a different orientation of the plane. Different grains have a different orientation of a particular plane. So because of this orientations, we can see that, you know, Bragg's law, okay? Because of the Bragg's law, that incident electrons is been diffract. Because of the diffractions, you can see the white line and the black lines. You can see this is the diffractions. As per the Bragg's law, the incident angle and the diffraction angle is same. Because of the diffractions, you can get informations about the stronger diffraction and the weaker diffractions. And basically in 3-dimensional, you can, this is another image, you can see, magnified image. From there, you can see the diffraction. Because of the diffractions in 3-dimensional, you get a lines. This is the time transmitted beam, and this is the Kikuchi line. This is the diffraction line. This is called Kikuchi line. And in 3-dimensional, it forms a causal cone. It's not been shown here, but 3-dimensional, it forms a causal cone. So as I was discussing, this is you can see one particular line. This line is almost more or less straight line, but basically it is not a straight line. but in three-dimensional, it is a straight line. It is visualized as a straight line. So each straight line corresponding to one particular plane. So the Kikuchi line give the informations about the plane. Okay. So from this line, if you know this is the screen. If you know the diffracted planes or the specimens, and if you know the distance from the distance of the phosphorus screen from the sample, then with the help of this simple calculation, you can find out. And if you know the angles, as I already mentioned, it could be any angle, 60 to 70 degree. If you know the angle, then you can find out the distance between distance between the incident beam and the diffracted beam. If you know this distance, this gives a crystallographic information, and from there you can calibrate or you can understand the distance between two planes or distance between two identical planes. So here HKL, some sort of plane is
Sir, your voice is not audible.
Sir, your voice is not audible.
in the middle, it was disconnected. How much you have understood? I don't know. Yeah. What I was discussing, that if you know the HKL value, from there you can calculate the D value. From the D value you can calculate if you know the distance between the incident beam and the diffracted beam. Basically, if you know the distance between these two, then from there, with the help of these equations, you can find out the distance D, and from there you can find out the HKL informations. Basically, you can find out the informations about the crystal structure. Okay, and from there, you know the different plane have a different orientations, and because of that, the Kikuchi line having some different orientations, and from there we can find out the D value as well as D mean crystallographic distance, as well as you can find out the microstructural orientation from this angle. Okay, basically from there we can find out the complete information about the texture. What is texture mean? Texture means if you see the less texture sheet, like if you know the any plates, any sheet metal or plates consist of some sort of grains, each grain having different crystallographic orientations, or rather we can say the each grain having different orientation of the planes. Okay, in the meantime, if you have any doubt, you can stop me and ask me. Okay, so you know each grain having different crystallographic orientations or the orientation of the plane. Because of that, if it is a less texture material, then in a pole figure, or if you want to see any particular plane like 111 planes. This plane has random orientations, and that is called lace texture material. But if you see any particular material having all the grains is more or less fully texture, or the orientation of a particular plane like 111 plane is more or less oriented towards the any particular direction like ND, RD or TD direction. That is normal direction, that is rolling direction, that is transverse directions. So if any particular plane is oriented any particular directions, and that is called texture sample or texture sheet. Like here, you can see all the crystal, like cubic crystals, are oriented more or less homogeneously, and that is called texture. And normal material which is not having any texture, that in that case the grains are not oriented in a particular directions. You can see each grains have in a different directions with respect to RD. For example, here you can see alpha titanium and beta titanium. Beta titanium have different crystallography and alpha titanium have different crystallography. Beta titanium is BCC in structure and alpha titanium is HCP, hexagonal close pack structure. So because of that, you can see even though the incident angle is same, the Kikuchi patterns is not same. You can see Kikuchi pattern have difference because of two reasons. Because of difference in crystal structure like D value, A, B, C value, okay, and as well as the difference in orientation. In case of HCP, it is 60-degree orientation. In case of BCC, it is 90-degree between two planes. So because of this difference in orientations, you can prove each element in a phase map. This is the phase map. It identifies different phases, and different phases has been colored in different color. So because of that, you can easily find out how the different phases has been dispersed in a particular material. So like here you can see, even this is the single material like beta titanium. When you only try to find out the information from the beta titanium from this phase map, you can see this is the beta titanium and this is the alpha titanium. You can differentiate which portions in your material has beta characteristics or beta titanium characteristic, and which portions in your material having alpha characteristics. Okay, so you can see this is the hexagonal structure and this is the body center cubic structure. Okay, so basically this is the power of EBST. You can get a lot of informations, not only the information about the orientations. In addition to that, you can find out the informations about how the distribution is there in the material and what is the grain size, or is there any, what I can say, is there any phases present or not? Is there any residual stress developed inside or not? There is a lot of information you can find out. Now I'm coming to the application part. I have been working on dissimilar level, how I use this all sort of characterization technique in dissimilar level. That is the information I'm trying to give in this part 2. First, many of you may have familiarity with friction stir welding, but for the people who does not have any understanding about the friction stir welding, let me just take you to these animations. You can see this is a rotating tool and this is the tool material which is placed in a part joint configurations. And this rotating tool is continuously rotated, is plunged into the material. You can see the pin portions is inserted into the material not the solder portions. Then you traverse it, and because of the frictions develop between the material and the tool, the material gets softened and material get heated up, and because of this heating, you can see when it is inserted, the probe is inserted, not the solder. Solder does touch the sample, and after that you traverse the tool. Because of the traversing, the frictions develop the heat, and because of heat, you can see the red color. Because of heating, material gets softened. You know, when the material gets plasticized or softened, it is easy to move around. And because of the rotation, the softened material from both the sides move around the tool and it get mixed. And because of the mixing, the welding takes place. Okay. And this is some of the terminology I have used, that retreating site, advancing site. Advancing site means where in this direction, in this side actually, the advancing site, the rotational vector of the tool and the moving or the welding direction is same. And that's why it is called advancing site. So there are various advantages are there. There is no melting, and that's why any defect arise due to the solidification during fusion welding does not come into pictures. And any problem associated with heating or the high temperatures developed during the process will not come into pictures. In addition to that, you can get a recrystallized microstructure. You know, when the material gets recrystallized, the ductility of the material increases, but the tensile strength in general decreases. But here, because of the severe plastic deformations, it is not only the temperature evolution. In addition to that, there is a rotation. Because of the rotation, there is a severe plastic deformation take place, and it is a dynamically recrystallized microstructure developed in the weld nugget, and hence we get a very good combinations of mechanical property. And there is no fume evolved during the process, and that's why it is environmental friendly process. But the problem is the costlier than the conventional manufacturing process, conventional welding process. Okay. And I have been working on aluminum titanium. If you see the aluminum titanium phase diagram, you can see not only the solid solutions develop, in addition to that, there is a lot of intermetallics developed during the process. You know, intermetallic is very, very brittle material. Okay. So any weld which include intermetallics have problem associated with failure. Okay, easy failure or sudden failure. So it is advisable to avoid the intermetallic formations. And this sort of welding is very, very useful in aviation industry. So that is the project we got from DRTO. So to avoid the intermetallic formation and improve the mechanical property. And there is many locations where this welding is very, very important, like seat track, skin stringent fuselage, hybrid structures being used in aviation industry. So there it is very, very useful. If you see the property of aluminum and titanium, you can see the aluminum is FCC structure, titanium is ACP, alpha titanium, and beta titanium is BCC structure. Because of the difference, not only in the crystal structure, you can see the melting point, density, heat conductivity, and coefficient of thermal expansion. This is very, very important, coefficient of thermal expansion for the defect point of view, because during the solidifications, because of the difference in the linear thermal expansion coefficient and linear thermal contraction coefficients, the defect arise. Okay. So basically, due to the difference in the property, physical and thermal property, it is very, very difficult to get a proper good joint in conventional fusion welding process. because of solidification defect, because of formations, because of evolutions of the residual stress, and in addition to the difference in the thermal behavior from the aluminum side to the titanium side. In addition to that, if you see the flow stress behavior of the material at a different temperature, you can see there is a lot of difference in the flow stress behavior. Okay, when it is subjected to high temperatures, subjected to at a different temperature and different strain rate. And because of that, you can understand in that one side, when tool is rotating, one side, the tool may subject it to wear and tear, and the other side, it is not. So there is a inhomogeneity, not only in the material property, inhomogeneity in the load bearing capacity of the tool from one side to the other. So tool could be subjected to wear and tear, as well as vibrations, and as well as fatigue property. So because of the rotations. And in addition to that, at the interface, you can see the titanium, and this is the aluminum in interface. It is possible to formation of different kind of defect because of this is the layer structures. Because of the layer structure and because of the difference in the thermal expansion and contraction coefficient, the line defects, you can see micro defect, even this is the micro defect that could come into picture in the weld structure. So there is a few informations about the solid state welding, that is friction stir welding, and there is a different problem people have come across, like what I have shown here. This is the swirl-like structure. This is the swirl-like structure. This is the intermetallic structure. Okay, and this is the variation of the microstructural property from the aluminum side to the titanium side. So that actually play a role in defect formations during tensile testing. As I already discussed, that intermetallic formations is another problem which need to be countered by process optimization technique. So the main objective is to optimize the process parameter, then understand the three-dimensional behavior of the weld structure and how the joint form, and that only you can find out, that only you can understand when we try to understand the deformation behavior of the material like titanium and aluminum. And already you have seen that during the formation of the intercalated structure or the swirl-like structure, that titanium particles or titanium structure is fragmented. Here you can see the titanium is basically fragmented, not the aluminum, because titanium is high temperature material. So it gets fragmented during the deformation process. So you have to understand how this fragmentation taking place. And the deformation mechanism of aluminum, because aluminum gives that higher ductility in the weld structure. And overall, you have to find out the mechanical property, and then you have to investigate that whether the structure which has been developed, it's stable at high temperature or not. If you are able to find out the stability at high temperature, the same microstructure, which is actually the composite sort of microstructure, then you can also find out the information about the composite behavior of the material at higher temperatures. So this is the different process parameter in friction stir welding: interface positions, tool rotation speed, tower speed, tool tip angle, depth of penetrations, and this is the informations about the temperature evolutions. This is very, very important, because since it is a solid state welding process, it is expected the temperature should be lower than the melting point of the material, and that actually depends on the process parameter. And this is the RPM of the tool, this is the welding speed, and this is the material constant. So basically, this is my experimental plans. We have done the microstructural characterization, mechanical characterization after the friction stir welding, and this is the total overview of the total overview of the process optimization technique. We have used different process optimization technique that is called, for example, bottom-up approach technique and as well as design of experiment technique. Just for example, I have given, see that depending on the process parameter, this is the traverse speed or the welding speed, you have varied the welding speed, you have seen the different structure. So here you can see that the big block of titanium particles has been disintegrated from the titanium site. And this sort of block or formation of block in the weld nugget is a critical things. So we should avoid this thing because the interface of this block or interface of the flake, interface of titanium aluminum is critical point in terms of formation of crack during the deformations as well as during the tensile testing. So we need to avoid this sort of formation of block or this sort of formation of flake. So therefore, we have come across some sort of weld with proper weld nugget. So we can see the number of blocks is very, very small, or you can get a very good fine distribution of fine particles in the weld nugget. This is the titanium side, this is the aluminum side. And we have done the mechanical testing. From there, you can see that at 90 mm per minute, we get a very good mechanical property. And the efficiency is close to 100%. So if you try to come across, or if you try to understand the structure property relations, first you have to understand how the structure has been developed. And if you want to understand the structure of the microstructure development mechanism, then you have to find out the two things. One is the process parameter, and second thing is the temperature. So process parameter already you have optimized, and during the process you have find out the temperatures increase as much as 410 degrees centigrade. This is the lower limit of the temperature, and we have also seen the temperature could increase up to 450 degrees centigrade. So this is a very, very low temperatures in terms of if you think in terms of welding of titanium. Okay, and this is lower than the melting point of the aluminum as well. You can see, but how it is possible then when you are welding or when you are deforming the titanium, then the temperature during the deformation process is as low as 450 degrees centigrade. So then we have seen, to understand the mechanisms of temperature evolutions, we have seen the tool interface as well as the process zone interface, and we have seen that aluminum is coating the processing zone. You can see diffuse interface, and this is the titanium side, and this is the process zone. On top of the process zone, you can see this is the titanium, this is the aluminum, and you can see the tool surface also. You can see the coating of aluminum. So basically the coating of aluminum, basically at 450 degrees centigrade, aluminum get recrystallized. This is the understanding we have developed, that at this temperature aluminum get recrystallized. Because of the recrystallizations, it get plasticized as well. Because of plasticization, because of plasticity, because of low flow stress of the material, that aluminum squeeze out of the process zone because of the force imparted by the tool, and then this aluminum squeeze out and form a coating on the top of the surface. So basically, this is the interaction between the aluminum and the tool, not the titanium with the tool. And even though there is some sort of interaction with the titanium, but it is not substantial. So since the frictions develop between the aluminum and the tool, and we know the friction generated temperature never ever reaches the melting point of the material, because at melting point coefficient of friction value is come to 0. So therefore the temperature never reaches the melting point of the material, and therefore the temperature which has been estimated in the present form, it is correct. And this is the schematic view of the process zone. One side there is a titanium, and the side there is a aluminum. At the center we got process zone of aluminum. This is the metal matrix sort of composite material developed at the interface at the wheel nugget, where the titanium particle has been distributed. Why the titanium particle form? Because it's the low temperature deformation process, and because of the deformation at low temperature and high standard, titanium get fragmented and it is distributed in the oil nugget. So basically I was trying to say that it is not only the titanium particle, it's initially maybe it is titanium particle. During the deformations, the titanium particle as interact with the aluminum and it converted to some sort of intermetallic as well. So you can consider this structure as a metal matrix composite where the titanium particle and the intermetallic particle is distributed. I want to add another point is that due to the steering actions, due to the rotation of the tool, even though the intermetallic form at the joining interface, and as we know, the intermetallic is very, very brittle. Okay, so during the deformation process or during the rotation of the tool, the intermetallic which has been developed at the interface is subjected to fracture, and this particle actually distributed in the metal matrix, which is the oil nugget zone. And same has been shown here in this is the coating, and this is aluminum coating. Titanium fragment is distributed in the oil nugget zone. And during the calculation of the temperature, we have assumed that below the tool shoulder, the temperature is homogeneous. So to understand that assumption, whether it is more or less correct or not, we have done a simulation process, that friction state simulation using processing simulation using deformed 3D with the help of same material. So you can see the simulation process. Here the tool is not been shown here, tool has been discarded or omitted, so that you can understand how the deformation process takes place. So here you can see in the advancing zone, the material, see here the material actually get joined together in the advancing side. So this is the deforming material and which has been joined to the advancing side material. And another point is that below the tool shoulder, temperature is more or less homogeneous. This is the tool shoulder zone, this is the red color. So in this location, temperature is more or less homogeneous. So our assumption is correct. So this is the normal ACM microstructure. You can see the deformations behavior. This is the base material behavior, and this is the deformation behavior, deformation microstructure of the aluminum. And this is the oil nugget zone, you can see. And as I was discussing, that particle get fragmented during the deformation process as well. You can see the fracture. This is the original particle which is get fragmented continuously. You can see this is the fragmentations of the particle in the oil nugget, and this is the intercalated structure we have observed in the microstructure. And you can see there is a particles is not a completely titanium particle. This is the BSC image. From there, from the contrast, you can find out the elemental compositions. You can see from the particles contrast. So this is not a complete titanium particle. There is some reaction been taking place, and it is expected to formations. It is expected to subjected to some sort of chemical reactions, which generally lead to formation of intermetallics. This is same thing. From the compositional analysis, you can find out this is the particle, and from the titanium aluminum compositions, and this is the jet compositions. Jet mean the equivalent atomic contrast. From there, you can easily find out this is not a complete titanium particle. This is a intercalated particle or the mixed particle. You can see, and see the flow lines. You can see this is the flow lines. From the compositional analysis, you can also study the flow lines. You can study the mechanically mixing behavior. You can study the compositional analysis, or as well as you can study the reaction dominated fracture behavior as well. Now I'm coming to the advanced characterization, what I have done during the process. You can see friction stir welding of aluminum titanium. Already I have shown the microstructure. This is the same microstructure I have shown here in figure A. And after the tomography, we have got this sort of microstructure. Okay, this is the informations of the distribution of the titanium particle only in the weld nugget. So you can see this is the interface, and this is the particle which has been distributed. This is the random distribution. You can, by observing the three-dimensional structure, you can see this is the random distribution. If you see the video of this tomographic image in 3D, you can see this is the inhomogeneous distribution. There is some particles of different shape, okay, and particles are randomly distributed. Some particles are elongated, some are very fine particles, and mostly you can see from the contrast that in the top side, the very, very fine particles might be present. Okay. So then this is the two-dimensional image, okay, of the same thing. This is a projection of that in two-dimensional. But when we have characterized the each locations from the top to the center, rotating side to the advancing side, we have found out a very interesting trend that each locations, the particle distributions is something like this, which is shown in this figure. From there, we can find out that as the particle size decreases, the number of fractions increases. That means the same thing, that initially might bigger particle form, which is subjected to fragmentation continuously, leading to the formation of very, very fine particle in the structures. And that is true not only for a particular location, that is true for complete weld nugget. This is very interesting. Why? Because we know that in a composite material, if you want to improve the mechanical property, it is advisable to introduce or decrease the size of the second phase particles so that you can get a better mechanical property. So if our weld structure is also have the same sort of microstructure, and if I want to improve the mechanical property of my weld, it is better to introduce very fine particles, or even though it's formed in situ, if somehow, if you can increase the number fraction of the fine particle, then we can get a very good mechanical property weld. So how you can do that? Okay, that is the one question. And second question, is it possible to find out the mechanisms of the particle formations? If I can find out the mechanical of the mechanisms of the particle formations, then by some other method, we can improve or you can increase the number of fractions of the fine particles by fragmenting more. For example, if I find out that this is associated with some sort of stress behavior of the material or applied stress, then you can increase the stress to get more fine particles. Okay. So therefore, the first option is to understand the mechanism. To understand the mechanism, yeah, the same thing we have also differentiate the particles with their volume fraction or their particle size. You can see the fine particles are homogeneously distributed. This is another important factor. The fine particle could be homogeneously distributed, unlike the coarse particle. Okay, if the particle is homogeneously distributed, then we can get a better homogeneous property or the repeatable property from the structure. Okay, so this is another information. To understand the mechanism, we have done the EBST characterization technique on the titanium side, because we are we are looking for understanding the mechanism of particle fragmentation of titanium. Okay, so we have understood that the titanium, you can see homogeneous structure, and this is the grain informations from the EBST structure. You can see I have, you know that what is called high angle grain boundary. High angle grain boundary having the orientations more than 15 degree, then it is called high angle grain boundary. If it is less than 15 degree, that is called low angle grain boundary. And if it is less than 5 degree, in my case, I can say it is not even the grain boundary, it is just formulating or it is evolving to be a grain boundary, and that is called sub-grain boundary. So you have demarcated the three type of grain boundary, and 2 to 5 degree, 5 to 15 degree, and above 15 degree, and I have marked with a different color. From this color informations, we have found out that this is homogeneously distributed. The grain boundaries are homogeneously distributed. This is the clear signature of the recrystallized microstructure, because in the recrystallized microstructure, the any informations is homogeneous. Okay, this is the new formation of a grains. Okay, so it is a homogeneous sort of microstructure we generally see. The same information from CAM map. This is the CAM map. It gives the informations about the orientations of each pixel. Okay, at each point you can see this is the image. At each point, how much is the orientation deviation from the neighboring points with respect to the neighboring neighbors. That is the informations we get in the CAM map, and that is equivalent to the dislocation informations. So the people who are from the material backgrounds, they are very familiar with the dislocation. Dislocation is nothing but the absence of atom. So there is, when there is an absence of atom, there is a orientation deviation, and this is the energy associated with this. So that information also you can find out with the help of EBST or the CAM map of the EBST. And this is the Gauss map. It is give the overall orientations, deviations of a grain. So this is the structure. You can see this is the image of different grain. So each grain having a different, each grain is consist of a number of pixels. So each pixel have a orientation deviation that we have find out from the CAM map. So the number of pixels in a grain having certain orientation deviations. So each grains have certain pixel, each pixel have orientation deviation. So average orientation deviations of a grain has been characterized with the help of Gauss map. we can find out is the grain orientation deviations. From that, we can find out the how many grains are actually recrystallized. It is possible that when you are deforming a material, it is deforming a material if it is not homogeneous deformation. If it is a heterogeneous deformation like rolling, forging. So each grains is not subjected to equal amount of stress strain. Okay, so then the behavior, the deformation behavior varies, and if the material is subjected to high temperature or heat treatment condition, you know, if you not give the proper times, if you not optimize the time and temperature, then material may not, each point in the material may not subjected to equal amount of thermal cycle or the same thermal cycle. So then there are the deviations in the microstructural evolution. So that deviation in recrystallization, deviation in residual stress and development. So that information can be found out from Gauss map. So here you can see the average deviations 0 to 1, 1 to 2, I have just pointed out with the help of different color. So if the average deviation is very, very less, like close to 0 to 2, then it is called a recrystallized microstructure. That means the average deviations in a grain is very, very less, which is a clear signature of the recrystallized grain microstructure, because in a recrystallized grain, there is no residual strain. There is limited amount of residual strain or the dislocation density. Okay. So this is the information we have find out from the EBSD map. And then we are trying to find out the mechanisms of the deformations. Then we have characterized the titanium base metal microstructure. You can see there is a limited amount of twin formations. That is a typical signature of HCP type of material when it's subjected to subjected to different thermomechanical process. So if the temperature is very, if the material is subjected to high amount of deformation, which is seen here, the number of twins increases, and this is the titanium microstructure, which is found out close to the interface. And this is the at the interface. You can see this is the aluminum, this is the titanium. There is some gap. The black lines is not only gap. You can say it is a gap. This could be cracked, or this could be some sort of other material, like it could be intermetallic particles. I have just mapped the titanium and aluminum, not the other material. It could be other intermetallic or some other phases. So therefore it is coming as black. But in my case, since it is a welding form and we have already seen the microstructure in ACM, then we can easily say that this is not a crack, this is a intermetallic form. But this is sort of things which is generally developed because of crack formations. So we can say that because of the crack formation, that intermetallics developed. Because of a crack formation, aluminum enter into these locations, and because of the reactions, chemical reaction between aluminum titanium intermetallic form. So you can see that there is a very, very fine microstructure even compared to the aluminum. Okay, and from this grain boundary map, you can find out this is homogeneous grain boundary distributions. There is no intergranular orientation deviation. So we can, from the Gauss map, we can see it is more or less recrystallized. As I already discussed, 0 to 2 is a recrystallization. So from there we can understood that this is the fracture being taking place on the titanium side. In addition to that, there is a recrystallization. So this is the same thing we can find out from the ACM microstructure. We can see this is the interface, this is the particle, the fragmentation taking place on the titanium particle as well as in the interface. And this is the crack being developed, which has been propagated into the material, inside the material, and you can see this new particle form. And this is the onset of the particle formations. And this is the recrystalline microstructure, the fine grain you can see from the ECM microstructure. So from there we can come out the mechanism of adiabatic shear band formation in titanium interface, and that led to the recrystallization as well as the crack formations. And because of the enhanced kinetics of the recrystalline microstructure, or even the particle which has been formed here, you can see there is a high surface to volume ratio. Because of the enhanced kinetics, it leads to intermetallic formation. So that's mean the particle which is very, very fine, it's easily converted to intermetallics. And because of this intermetallics, it actually distribute. And it actually distribute as a dispersoid in the weld nugget and could lead to improve in the mechanical property. So this is the TM microstructure. You can see the very, very fine recrystallized microstructure being formed, the adiabatic shear band form. So this is the adiabatic shear band. You can see this is the band structure. If you have a close look, you can find out very, very recrystallized microstructure without any formation of dislocations. So this is a clear information that base deformations lead to crack formations as well as recrystallization that we have seen in our EBSD microstructure. You have seen EBSD, this is the recrystallized microstructure, and that mechanism is adiabatic formations in titanium interface. See, this is the adiabatic shear band formations. In the microstructure, this is the tomography image. From there, you can see how the adiabatic shear band form, how the crack develop inside the particle. See, this is the particle. You can see how the crack been formed. And this is the layered structure. This is the adiabatic shear line formed in the titanium interface. And this whole mechanism has been schematically shown here. Initially, there is an adiabatic shear band formation ahead of the tool, okay, and that lead to formation of particles. In the aluminum side also, we have seen the similar sort of microstructure, that is the recrystallized microstructure, okay. And if you see some sort of grain boundary, you can see there's a mixed character. So see, here is a green and the blue character is mixed together. Here also see blue and green. So this is the location. You can see here these locations, red, blue and green. All three color is available. Three type of grain boundary has been seen in a particular locations. So this is the clear indication of grain boundary evolutions, and this is represent the continuous dynamic recrystallization mechanism that is very, very easily observed in aluminum because of high stacking fall energy of the material. And you can see the 78% grains, like 0.022 Gauss value, you can see that 78% grain are dynamically recrystallized. That clear information that the Welds nugget is very, very soft, or it is the matrix material, which is aluminum, which is dynamically recrystallized, on which the particles, this is the particle you can see, this particle or the second phase particle are distributed. And if you characterize further, or if you take this Gauss map and if you differentiate with respect to their grain size, okay, different grain size, you can see this is the fine grain, this is the coarse grain. Okay, the coarse grain structure, we could not see the blue color much. Why? Because coarse grain structure is subjected to fragmentations or evolutions during the continuous dynamic recrystallization. And in case of fine grains, you can see this is the fine grains. Fine grain is completely recrystallized because it is evolved already during the process, lead to the fine microstructure. And this is the clear informations or clear evidence that the continual dynamic recrystallization is the dominant mechanism in aluminum during the welding. So then we have done the mechanical property study, and we have got a very good mechanical property, and we have correlate the structure which has been developed in the material and the property. And this is the tensile property, and see the fracture behavior. We can see very good ductile kind of fractures, as well as when the particles are there, we observe brittle kind of fracture. We have obtained a very good fracture property or the fatigue behavior of the material as well. This is just a fractograph. Okay. So the first information we have got, that mechanism we have understood. With the mechanisms, we can say that if you deform the material or deform the particle further, the particle get fragmented more, and therefore we can obtain a higher fraction of fine particle in the oil nugget, which could lead to higher mechanical property. So to characterize or to prove our observations correct, we have done a second pass. On top of the first pass, we have got a very good mechanical property, and we have understood the mechanical property, why the mechanical property is higher. Not only the tensile property, as well as the ductility, we have come across a spring model. We have correlate the microstructure. This spring model has been developed from the microstructural point of view. You can see from the microstructure, we have seen that after the second pass, the intermediate layer thickness increase, as well as there is a particle fractions. We have correlated the microstructure. We have find out very good correlations, structure property correlations during the welding as well. So I'm not, see here, I'm trying to say that not only the two-phase component we can find out, even we can see the multi-component structure. Here we have used the niobium as an interlayer material, and we have seen the orange color is actually the niobium particle. We can also trace how the niobium particle are distributed in the weld nugget. You can see, let me do again. This is the weld nugget, or this is the weld interface, and this is the bottom side, this is the top side, this is the particles, and also you have seen that this is the particles are, see, this is the niobium and this is the titanium particles. We can see the interactions, and there is some sort of reaction taking place between the niobium titanium as well. So if niobium titanium interact or chemically react, which is very good, because niobium titanium give very good what I can say, very good solid solutions. So then titanium alumina interactions is substantially reduced, and that lead to reduction in the brittle intermetallic formation, and hence we got a very good mechanical property as well. And this is the ABAG structure. We can find out the layer, different layer based on their orientation, based on their grain size, and we have come across not only the CTRX is present, but also other mechanisms like particle stimulated mechanisms and discontinuous dynamics also present in the microstructure. So this is the summary of whatever we have discussed. Now I'm coming to the second part. This is the effect of particles in high temperature cane stability, titanium particles. So this is the microstructure cross-sectional. Cross-sectional view we can see, and from there you can see that particles are homogeneously distributed in the weld nugget, and when we have characterized the interface, this is the mechanically mixed zone, or the particle where are distributed. This is the particle where, this is the aluminum where the particles or the fine particles are not distributed. So we have this microstructure has been subjected to high temperature or heat treated at high temperature. We can see where the particles are distributed is thermally stable, or grain are highly stable compared to the location where particles are not distributed. So this is the tremendous improvement we have achieved when we have used the zinc as an interlayer. So this is the same thing that even though this is recrystallized microstructure inside the mechanically mixed zone, even at high temperature heat treatment, the grains are highly stable. So from there we have come across, we have done in-depth characterizations. We have seen the particles which actually restrict the grain boundary mobility. This is not only the titanium particle, this is the intermetallic particle mostly, because this is the fine particles. So fine particle actually easily converted to intermetallic because of higher kinetics, and that actually pin the grain boundary mobility, and which is much more effective than titanium. Similar thing we have observed when we have done welding of aluminum titanium. Here that the titanium particles are distributed, we have observed a huge grain stability, substantial grain stability at high temperature. Okay, even though the grains are highly recrystallized inside the mechanically mixed zone, generally we have seen that if grain are highly recrystallized, is easy to grain growth. It is prone to grain growth, but because of the particles which are distributed, the fine particles which are distributed the grain boundary, restrict the movement, and hence the grain stability increases. So this is the mechanism what I have discussed. You see very fine particles pin the grain boundary mobility. So this is the TM image. From the TM image, we can see that this is the fine particles and this is the grain boundary. Okay, so grain boundary actually hindered fine grain actually hindered the grain boundary mobility. This is the summary of this chapter, that high temperature grain stability of aluminum grains in the process zone is enhanced due to the distribution of the titanium, fine titanium and intermetallic particle. That is very, very important. And it is influenced by the not only the distribution of the particle size, also the particle size is very, very important in addition to the distributions. And we have also observed that if the fine particle, which is basically intermetallic particle, being distributed, which can be highly effective in terms of high temperature grain stability of aluminum composite material in comparison to titanium particles, because of high temperature grain stability of titanium itself. It does not degrade its property at high temperature. So this is a few of the references which you can refer to have a clear understanding or in-depth understanding of the process of the information I have put here. So thank you for your kind attention. So I'm happy to be here, and I hope that our interaction will continue. If you have any doubt, you can ask me, or you can send me emails later as well. So I hope this is the new beginning of our interactions. Thank you.
Yes, participants, if you have any doubts, you can just unmute yourself and then ask the queries to the speaker. If any issues with the unmuting, you can even write in the chat box. Yeah, meanwhile, I have a question. You have done the heat treatment after post welding, post friction stir welding, right? Mm-hmm. So have you checked in on mechanical properties after post welding?
Yeah, we have checked the mechanical property. Mechanical property is improved. If you talk in terms of only in the oil nugget, not the total oil structure. Yeah, so this mechanism is also applicable for composite material. Okay, So we have studied the mechanical property of the only the oil nugget locations or the process zone locations. Then we have seen that mechanical property is substantially good. It is more than the base metal property because of Hall-Page equation, you know. Okay. Probably that is the effect.
Yeah, because in post welding heat treatment, we got a equiaxed grains also. So that should have enhanced the properties. So that is what I have asked. Like,
yeah, in our process also we are getting more or less homogeneous microstructure.
yeah.
Okay.
And another thing, like when aluminum and titanium were being friction stir welded, the titanium fragments which are there at the nugget zone, because of this intermetallic kind of a particles, in terms of ductility, it is very low, right? How shall we address those things?
Yeah, ductility generally it is low, but that's why I'm telling that ductility is depend on the formations of crack or the beginning of the crack formations. If you can tackle that, then you can get the improvement in the mechanical property. In my case, what we are doing actually, we are trying to, that's why you have done the optimization process. Initially, I have discussed. So if you get a very good mixing of the particles in the oil nugget, very good mixing as well as the size of the particle is small, okay, then behave like a composite mixture or it behave like a metal matrix composite, okay.
Okay.
And since metal matrix composite generally give very good tensile property, and in addition to that, here we are getting the aluminum microstructure, which is ductile in nature.
Ductile, yes.
Sorry, which is recrystallized. So it give a very good ductility. Okay, so this is therefore we are getting the combinations of the mechanical property, and hence we are getting the very good overall mechanical property.
Okay. Yeah, thank you very much. One more question is from the chat box. Participant is asking, sir, what is the use of suit and operand leaching methods in X-ray MCT?
What actually? Can you repeat the questions?
Yeah.
I just stopped the sharing so that I can also see.
Yeah. Sir, what is the use of suit? And I hope it is in suit or X-suit. I don't understand. Like use of operand leaching methods in X-ray MCT.
Actually I was talking about the in situ method.
Yeah, it would be
during the process, or in situ means actually during the process it develops itself. Okay, like for example, in my case, the titanium particle is developed during the process itself. We are not incorporating the titanium particle in the matrix material or in the well nugget. Okay, and actually it is operating condition I was talking about. So during the operation, like if you are trying to do the tensile test, so during tensile testing of composite material, okay, so when the fracture or the crack being developed, that you can probe with the help of X-ray microtomography method. So if your sample is inside the chamber of the XCT machines and you are doing the tensile testing, then so whatever the crack formation been taking place, it is inside the material. So that only you can track, the crack formation only you can track with the help of XCT method. Okay, so that is the in situ characterizations of the material, of the process. And that you can characterize with the help of XCT method as well as EBST method also people are using. But EBST method, you can understand that EBST method, the difference between EBST and XCT method, the XCT method is three-dimensional information. You are getting the three-dimensional informations. And for EBST method, you are getting two-dimensional informations. Okay. And EBST method, you can characterize the orientation variations during the deformations. Not only deformation during heat treatment, also people are tracking it. Okay. But in XCT method, you can characterize the informations which is been present inside the material. Even though in situ test, like in situ tensile testing condition also, you can study the process with the help of XCT method.
Hello, sir.
Yeah.
Sir, is XCT qualitative or quantitative method?
Which one?
Qualitative
Both
or
are quality based and quantity. You can quantify it is also. That I have shown here in my microstructure in my study, that you can characterize the particle size and particle size distributions. So you can see in the XCT method, you can see how it is distributed, and at the same time you can characterize how the particle size is and how many particles are there.
Sir? Hello? Hello?
Yeah.
Sir, can you explain once how can we determine the fiber length distribution in polymer reinforced fiber?
Can you repeat again?
How can we determine the fiber length distribution in reinforced fiber polymers?
Fiber length distributions.
Yes, sir.
And generally in fiber case, what I have not done, but what people do, actually fiber length, you can easily characterize with the help of EBST or XCT method. Okay. Then what they are generally do, actually distance, the distance between two fiber, that they characterize, they calculate. If you know the informations about the positions of one fiber and information about the second fiber, okay, then you can get the minimum distance between two fiber. Okay. So basically they are characterizing the distance between two fiber and see whether the distance between all the fibers are homogeneous or not.
Okay, thank you. Sir, one more thing is, sir, what are the commercially available XCT devices?
Commercially, I mean, Jessis fiber I have used. Okay. It's not commercially available. It is available actually. But this is popular. Jessis, you can get the information from the internet. I have shown some video, no? That it from this only.
Hello.
Yes.
Sir, as we saw that there is fine grains in the nugget region, and after that the intermetallic compounds are also formed. Then it will again increase the means it will again make it more brittle. So
You know about dispersoid strengthening composite? That
yes,
is
sir.
two type of composite. One is precipitation hardenable and dispersion.
Yes, sir. Yes, sir.
Okay.
Yes, sir.
In dispersion strengthening composite, what we do? We provide some sort of brittle material only, no? Like silicon carbide. So the mechanism is different. In this case, that Orowan strengthening mechanism, I think you might have come across this thing. Because of the Orowan strengthening mechanism, the more number of dislocation forms and dislocation interaction take place. Okay, dislocation can easily pass through that brittle particles. Okay, So because of that, even though these are brittle in nature, that improve the mechanical property. Only thing that you have to always look for it, that whether the particle which is brittle in nature is well distributed or not. This is very, very important. It should not, it should be homogeneously distributed more or less. Okay? Then it gives the better mechanical
The
property.
dislocation should not. Okay.
In case of dissimilar weld, if the intermetal, like generally in any welding, fusion welding process, the intermetallic form at the interface is a line component. Okay, there is, because of this line component form at the weld nugget. So if there is a crack formations in this particular location in the brittle zone, that easily propagate and lead to the sudden failure. Okay, but in this case, the particles which is there is distributed in the aluminum matrix. So even though there, if it is formed some sort of defect or some sort of crack at the particles, that could not propagate to the next particles because of aluminum presence in the matrix material. Understood?
Yes, sir. Thank you, sir.
So if you think about in terms of dispersion strengthening material, dispersion strengthening composite, then you can understand very easily.
Yes, sir. Means
Okay.
it's not pinning the dislocation movement and dislocations.
It is pinning the dislocation moment as well as it is generating more dislocations.
Okay, sir.
Okay.
But it allows to pass dislocation through it.
Yeah. It is not hindrance. It is not giving the complete hindrance.
Okay, sir.
Okay.
Okay. Thank you, sir.
Thank you.
Anybody else? Is there any participant who's like to clarify? Else you can even mail to Dr. Amlan Kar. He's very friendly and student friendly. Okay. So thank you, sir.
Thank you, Mahesh. Mahesh, anyhow, Mahesh is my batchmate, so I know him very much.
Yeah.
Okay.
So let me thank on this occasion Dr. Amlan Kar for his detailed explanations and a very good interaction session we had. And the session was very nice, where we had understood a lot details about the friction stir welding and the intermetallic compounds and all. How does it form and the process parameters. So it was a very great session that we had today. And thank you, Dr. Amlan Kar, for kindly accepting our invitation and being with us. So thank you very much, sir.
You know, just, yeah, thank you. Thank you. See you again. If anyone you have any doubt or anything else, you can mail me directly. Okay.
Yeah.
So
Thank you very
I'm
much.
just putting my mail ID here. Okay. So thank you all. Thank you, Mahesh.
Yes, sir.
Happy to have any interactions.
Yeah. Thank you very much. So all the participants will again meet at 3 o'clock in the afternoon session. Thank you, one and all. Thank you, sir.